All right, our notes for today are going to start on page 101. We're going to be talking about two kinds of symmetry today, and the first kind is a kind that you have been familiar with ever since you were really small. When you were in kindergarten, probably, whenever you were first learning how to use scissors, your kindergarten teacher probably had you make some kind of little Mother's Day card or something like that for your mom, where you fold a sheet of paper in half and you cut out a heart. That is just basically symmetry, and lines of symmetry are the same. That concept does not change at all from however early you learned it up until now. If you look at this first example on page 101, they start with an isosceles triangle, right? It's not going to make a great card for your mom, but it does have a line of symmetry like that card does. And so they take this triangle, they put it over on a piece of paper, they fold the paper in half, and that's what this dotted line represents, and just show that it is the same as itself. This half matches this half. The left half matches the right half. And the reason that that works is because you have all of these parts that have corresponding matches on the other half. So you have this line that is the same length as this line. They're marked congruent so that we know that they are going to match up. You also have this angle, this base angle of this isosceles triangle, and it has a match on the other side. So if those two halves of the triangle match, then really all they're doing is they're drawing a line right down the middle. And the goal for a line of symmetry is that you have to make two exactly equal parts on either side of your line. So this angle that's up here needs to match this angle that's over here. That means that line of symmetry is going to cut that angle in half. So the line of symmetry is an angle bisector of that vertex angle on this particular triangle. It won't necessarily always have to cut an angle in half, but in this case it does. Also, since this line of symmetry goes through this base of the triangle, it has to cut the base in half. So it is also a bisector of the base. If it doesn't bisect the base, you don't have two equal halves on either side. It also has to have matching angles where it cuts this base in half. So this has to make two right triangles. So you have a right angle in here and you have a right angle in there. So not only is it a bisector, it's a perpendicular bisector, because if it's not perpendicular, then these two halves of the triangle are not going to be exactly the same. If one of these angles down here is 95 degrees and the other one's 85, they're not going to match up when you fold it in half like they did up here. So not every line of symmetry will be a perpendicular bisector or an angle bisector, but just kind of wanted to point out that those things are happening because those are some concepts that we have reviewed in the past. What every line of symmetry will do is it will provide a line of reflection. So we're going to put line of reflection over here, and that's what this pink line is also. We had been talking about translations, rotations, and reflections before we left for fall break, and a reflection has the exact same spacing, the exact same patterns on either side of that line. So this pink line that cuts our triangle in half provides a reflection from one side to the other as well. So really, all we're getting that's new in terms of what symmetry means is symmetry is a line of reflection that cuts a figure in half. We already knew it cut the figure in half. Now we're combining it with our definition of reflection. So let's flip the page and talk about some different lines of symmetry. At the top, they're on 102. So on 102, at the top, it says draw the lines of symmetry, if any, on each figure, and tell the total number of lines of symmetry that each figure has. So the first one is a rectangle. Somebody tell me how we could draw a line of symmetry that would cut that figure exactly in half. So, very good, down the middle, and your hand went top to bottom, so that's how I'm going to do it. I'm going to go ahead and number it as I go. I'll tell you why I do that a little bit later. Somebody else give me one. Okay. Yep, good. This way. Side to side, horizontal. And then some folks tried to suggest yesterday that we do diagonal, and that's a really good guess. However, let me explain why diagonal does not work. To explain it first, I'm going to show you rather than tell you by using a sheet of paper. So I'm going to zoom way out You don't have to get a sheet of paper and waste it on this. I'm just going to show you. All right, so this is a rectangle. If I turn it this way, it's turned the same way that this one is. And so what we're trying to think is, would a line from this corner to this corner make a line of symmetry? So when I fold this paper, I need to create a line that goes from this corner up to this corner. So I'm going to try to fold that so that these corners are both cut in half. And you can see I'm kind of having a hard time doing that because the paper is not going to line up that way. Okay, so there's our rectangle. There's our line that goes corner to corner. It does not make a line of symmetry because these two corners don't overlap when we're done. That's going to be true of all rectangles unless they're squares. Squares would work, rectangles do not. To put that into terms of geometry, I want to talk about it in terms of what a reflection is. So I'm going to use a pencil. You don't have to draw the pencil marks with me, but I'm going to go ahead and draw a line from corner to corner like we would try to be imagining.
For an interruption, teacher, please release the senior to the little theater at this time, and I need to take something to write with. Thank you.
Now, we've talked about how symmetry means that there's a line of reflection that goes through the figure. And we've also talked about reflections and how when I reflect, let's say this corner, I have to make it travel in a line that's perpendicular to this line of reflection. So if I were to start at this corner and I were to make a line that is perpendicular, I'm just kind of estimating perpendicular over here. I don't have a slope. So there we go. That's pretty perpendicular. That looks pretty much like a right angle. That corner should go somewhere out here instead of over here where we would want it to go. So we can verify with some like real world examples like the sheets of paper that I folded where the corners didn't match. We can also kind of verify with some mathematical properties that we've previously learned, but a diagonal is not going to be a line of symmetry on a rectangle. So we had a total of 2 lines of symmetry. The reason I go ahead and number them, it's a little more obvious when you have more lines of symmetry, but let's say you're on a quiz, you're doing a quiz, doing a test, and you're kind of in a hurry, and you draw all the lines, and then you're counting them, and you're like, 1, 2, 3, 4, because you see 4 little ends sticking out there, but there's really not 4 different lines. There's only 2 of them. You don't want to double count. It's more helpful the more lines you have. So with 2, it's not really hard, but like if you had 10 lines of symmetry on something, it would be more beneficial to go ahead and have them numbered. So that's why I number them as I draw them. Next example is this triangle. I really don't like this example. I wish that they would have given you some markings to let you know for sure whether it's isosceles or not. Personally, I don't think it is. So we're going to go ahead and mark that and that and that. Put those marks in your book as well. I could see how you would think it would be isosceles, but I've looked at it really, really closely and I don't think it is. I do believe that this leg out here is longer than this one over here. And if it is longer, then it's not going to have any symmetry at all. If it were isosceles, it would be the exact same example that they did on the previous page. It's another reason that I think it's probably scalene and not isosceles. So if I don't have any parts that match, there's no way that I can draw a line of symmetry through this because none of the triangle's features have matches anywhere else in the triangle. If you look at your rectangle, when we cut it in half top to bottom, this short end was going to match up with this short end. And when you fold it from side to side like this, the top long edge is going to match the bottom long edge. But there are no matching parts over here. So no matter how you fold it, it's not going to match up because all the pieces are different from each other. So what about this little L shape over there? There is a line of symmetry on the L shape. How would it go? Very good, corner to corner, just like that. Lines of symmetry do not have to be just vertical and horizontal. They can be diagonal at any angle at all. And this is an example of that. So this just has one line of symmetry. Any questions so far about lines of symmetry? All right, so let's take a look real quick at your IXLs for the day. One of your IXLs, which you might have started yesterday, is on lines of symmetry. Actually, let me just do this from your Google class because it's linked. There we go. All right, so draw lines of symmetry. When this exercise opens up, it's like the most elementary looking thing. Oh, I do have to go to Clever first. Don't be like me. It's the most elementary looking thing you've ever seen. You can see that letter U, and you're just going to cut it in half. Like that's literally all you're going to do is cut it in half. So what you do is you click on the line, and the line will jump to different set places. Here we go. So this might not be a U anymore when the page loads. There we go. Now we have an E. All right, so all you're going to do is you're just going to draw a line. So you click line 1, and you click where you want it to go. Notice it's got this little cursor thing, and it jumps around. It's not completely free moving. It does like snap into certain preset places. So you can put it wherever you want it. So I'm going to start there, and then just draw a line over. Right? When it snaps there, you can see that it's pretty straight. The next jump up would be very obviously not straight. The next jump down would also be pretty obviously not straight. So just make sure you're drawing straight lines and you should be good. That's pretty much the whole first level. Your next level, you have an equilateral triangle. So you would have more lines because all of your parts are matching. So I'm going to have a perpendicular bisector and an angle bisector with this line. And then I'm going to pick a new line. The way to get a second line is to hit the plus sign. And you're going to go from the corner to the middle of the other side. And then you need to do that again, from the corner to the middle of the other side. If you have multiple lines of symmetry, they're probably all going to intersect in the same spot. So if I have one line that's kind of, let's see, kind of like that, they're not all intersecting in the same spot, so I'll know I've done something wrong. If you're drawing multiple lines, they're all going to meet in the middle of the figure. And so the middle of the figure is just one spot. So if they don't all meet up in one spot in the middle, at least one of your lines is not drawn correctly, and it's probably just that you jumped a little too high or a little too low on one of these corners. Next level, which is the last one, I think. Nope, one more. It's a D, but it's turned weird. It's still the same that you've been doing. You draw your line, done, right? Very, very simple. Now then, in the challenge zone, this is where you'll have lots of different lines to draw. This is the kind of problem where if I were doing it on paper, I would number them as I go. So this is a regular hexagon. Regular means all the sides are the same and all the angles are the same. So I'm going to draw a line that cuts all of the sides in half, because that should be mirror image on either side. And see, that one's a little too high, so I'm going to change it. There we go. Oops, need to finish it. There we go. And then I go to my third set of sides. All right, and I've cut all of the sides in half. Am I done? No. What else can I cut in half? Good. Yeah. So I can go like from there to there across with the corners, because you can see across that purple line, it's going to have a line of reflection as well. So I'm going to do that for all of my opposite corners. And look at all those lines of symmetry. But you got to get them all, right? If you only do the sides, that's half the answer. If you only do the angles, it's only half the answer. So you'll need to make sure that you get all of them. So this is one of those examples where if I was drawing it out, I wouldn't want to try to go count all of these lines. I would number them as I go, because if I'm on a weekly check or a common assessment and I'm concerned about my time, I don't want to just go count and find 12 lines of symmetry, because really there's only 6. Any questions about lines of symmetry before we go on to other kinds of symmetry? All right, so then back in your book, the bottom of page 102, this is a new kind of symmetry. It's rotational symmetry. We talked about rotations before fall break. Rotations spin a figure around a certain point, and that spin just changes where things go. It doesn't change their size. It doesn't change, the length of lines or the size of angles or anything. It just changes location. So all of your rotational symmetry problems will typically be done around the center of the shape. So that's why that dot is there. It's to mark where the center is and to kind of help you visualize what's going on a little bit better. And in order for us to better talk about what's going on here, I want us to label each of these corners. So at the top, I'm going to put an A, and then I'm going to go counterclockwise and label B, C, D, and E. So label A, B, C, D, and E going counterclockwise so that we can talk about those just a little bit more clearly. So rotations are based upon circles. When we talked about rotations, we talked about how things traveled in a circular path. So let's think about first how many degrees it would take if I were to hold this down on the dot and I were to spin the star. How many degrees would it be for A to travel all the way around in a full circle and end up where it is? How many degrees? Yeah, 360. So all of our calculations with rotational symmetry are going to be based on this idea that there's 360 degrees in a complete circle. So it tells us over here that the angle of rotational symmetry is 72 degrees. And what that means is that's the number of degrees for one corner to map onto the next corner. It could go clockwise, it could go counterclockwise, but there's 72 degrees between each of those two corners. How do you think they got 72? How divided by what? Very good. Not 4. How many even sections? No. How many even sections are there on this star? 5. Yeah. So there are 5 even sections. So 360 divided by 5 is how they got that 72 degrees. So all you're going to do for rotational symmetry is you're going to figure out how many matching parts there are, and don't overthink it, don't overcomplicate it. For example, I usually pick points that stick farthest out from the center. So I've got 1, 2, 3, 4, 5 of those. That's all you do. So you're not counting like this side matches this side that matches this side. No, just different chunks of your shape. And there are 5 basic chunks in this shape. So we did 360 divided by 5. So 72 degrees takes one corner onto the next corner, but rotational symmetry doesn't just happen one time. It can happen all the way around that circle. So it's not just 72, it's every 72 degrees. So go ahead and write that in. Sometimes you'll be asked to list out from 0 to 360 all of the degrees of rotation that map the figure onto itself. And that just means, you know, how many different degree measurements will map one corner onto one of these others. So in this case, it would be 72, and it would be 144, and it would be 216, and it would be 288, and the next one would be 360. So those would be all of the numbers from 0 to 360. But you can have numbers bigger than 360 as well. It just means that it has spun more than a complete circle. So personally, I like to list my answer like this, every 72 degrees. But just be aware that this is also an acceptable way to answer that, is to actually list out the multiples of 72. All right, so let's look at the top of page 103. Talk about the rotational symmetry on these shapes. We've got a square. First off, if you don't have this mark down here, please put that on there. There's no way to have 4 right angles, 3 congruent sides, and the 4th one not match. I think it's just a typo in the book. Some years that they send the book, it has that line, and some years it does not. So if you don't have it, please draw it in. So what we're asking ourselves, we're starting with 360 degrees because everything can be spun in 360 degrees and look the way it started. So what we're trying to ask ourselves is, okay, how many different matching parts do we have? I usually go by the corners. So how many different matching corners do we have on a square? 4. So 360 divided by 4 is 90. So we're looking for every 90 degrees. Our instructions tell us to list the angles of rotation less than 360. So you would have 90, 180, and 270. But again, as I've already mentioned, you can have numbers bigger than 360 also. It just means that you have spun it around more than a full circle. Okay, this is that same triangle that I didn't like the first time, and I don't like it here either, but We're going to go ahead and make the same markings. That's our short side. Here's our medium side. Here's our long side. How many matching parts on this triangle do we have? Oh. How many did we have last time? 0. So if I don't have any matching parts, are there any ways other than 360 that I can spin it to make it match itself? No. So we're going to put none. And then in parentheses, we're going to put only 360. And that's how I'm going to write that every time it happens. Everything can be rotated 360 degrees and map onto itself. So it's not like a special number, you know. Not everything can be rotated 90 degrees. That's kind of a special thing. Everything can be rotated 360. So it doesn't have any special degrees of rotation, but it does map to itself every 360 degrees. I just want you to be aware that both of those things are going on in case you come to a question where you have to select all of the angles of rotation. I want you to realize that 360 can always be selected. So we're going to write none and we're going to write only 360 every time that answer occurs. All right, now we have this arrow. How many matching sections do you have on this figure? 2. Yeah, you got the top and the bottom, right? You got the arrow that points up and the arrow that points down. So we're going to take 360, and what are we going to do with that 2? Yeah. And so when we divide, we end up with 180. And it's every 180 degrees. But if we're just listing angles of rotation that are less than 360, we're only going to write 180 in there. All right. If you have a highlighter, I want you to highlight question number 4. Question number 4 is a really good question. This would be a good test question because it requires a couple of different things to be understood before you can answer it thoroughly. So the question is, what figure, not one of these 3, just any figure that exists, what figure could be mapped onto itself by any angle of rotation? You could rotate it half a degree or 359 degrees or anything in between. So what figure would always look the same no matter how you rotate it? Very good, circle. And the reason that that works for a circle is because it has an infinite number of matching parts. So we're going to put infinite, F-I-N-I-T, infinite number of matching parts. All a circle is it is the set of points that are all the exact same distance from the center of the circle. And so it's just the same distance all the way around that circle, or all the way around the center, I guess. So there's no angle to match up. The arc is going to be the same curve all the way around. Otherwise, it would be like an oval instead of a circle. So a circle is going to match no matter how much or how little you rotate it. Very good. Okay, so when we move on to describing symmetries, all that means is you're just going to talk about the different lines and the different types of rotational symmetry all at once without being really asked. So describing the symmetry, we're going to put out here line and we're going to put rotation. And I want you to, you can see that you've already got the answer down here, right? If you were to be watching this as a video, this would be a good time that you would pause the video instead of just breezing through and looking at the answer. Pause and see if you can match up all of the stuff that's supposed to go on here. So that's what we're going to do. We're going to pause, and instead of looking ahead and just seeing the answer, we're going to see if we can figure it out on our own. So I'm going to give you a second. First, draw the lines. And I will tell you that there's more than just these 2. There's some other ones as well. See how many lines of symmetry you can draw through that little 4-pointed star. lines did you get? How many? Crickets. 4. Thank you. So we got this one given to us. We got this one given to us. How'd you draw the other 2? Good. I see a chopping motion. That means like this. Very good. So you got 4. Notice there's 8 different ends, so be careful when you're counting them. You should number them 1, and then don't number that one, and then 2, and don't number that one, and then 3, and then don't number that one, and then 4, and don't number that one. So 4 lines of rotation, or 4 lines of symmetry. For rotational symmetry, you start with what number that everything uses? How many degrees would it take to spin this top corner all the way back around? Yep. And then we divide it by the number of even chunks. How many even chunks are there on this shape? 4, yeah. No question mark. So 360 divided by 4 is going to give us 90 degrees. Is it just 90, or are there other numbers as well? Very good. So it's every 90. So you'd have 90, 180, 270, 360, and so on. You could keep going. So what that means is, if I wanted to take this corner and I wanted to spin it up there, I would have to rotate 90 degrees counterclockwise. Or if I wanted to take it and I wanted to spin it down to the bottom, I would have to rotate it 90 degrees clockwise. Now, there are 2 different topics that the book really does not cover that they should have, in my opinion. And so I'm going to use this space down here at the bottom of the page to write in a couple of questions, and we're going to talk about those. If I'm taking the time to do this and write in extra stuff in the book, that means that you will for sure see this on a quiz or a test at some point. Weekly check, common assessment, quiz, test, tomato, tomato. So the first thing over here, put just Q for question. First question is, how many degrees of rotation would map vertex A onto vertex D going counterclockwise? Okay. It's a long question, but it's not going to be a super difficult question. We do, however, need to label our corners. So corner A is going to be the top. B is going to be like on the west. C is going to be at the south. And then D is going to be on the east. So how many degrees of rotation would map vertex A onto vertex D, but we have to go counterclockwise. So we have to go around backwards of the way a clock would go. So first question is, how many degrees would it take? Feel free to look at the question above. How many degrees would it take to map A onto B? 90. We just figured that out up here. We did 360 divided by 4 and we got 90. So then what would I do to figure out how many from A to D? Say divide, multiply. Multiply. What are we going to multiply by? How many times do I need A to jump? Total, I need 2 more times, so I need a total of 3, right? I need to make 1 jump there. I need to make 2 jumps there. I need to make 3 jumps there. So A has to travel 1, 2, 3 spaces away, and every space is 90 degrees. So 90 degrees times 3 needs to travel 270 degrees. Now, typically, the question usually has something to do with like a Ferris wheel, right? That's one that I see a lot because Ferris wheel is basically a circle and it has all these little points along it, and the points are evenly spaced out. So that maybe it's not actually a circle, maybe it's more like a 10-sided figure or a 12-sided figure. And, you know, somebody gets in the first car and their friend is 3 cars away. What's the angle of rotation between them? That's all this is. So there's 270 degrees of rotation between car A and car D on the Ferris wheel. right? You can imagine this being a circle and all these being linked. Yes, yes, very good. So all the way around, no matter where you start. If I start at A and I wind up at A, it's 360. If I start at C and I wind up at C, it's 360. Good question. Okay, second question. I'm going to use a different color so that my work doesn't run together. This question, would a rotation of actually no, let's not do 720. Let's do 1080 degrees. Map the figure onto itself. Now, on a question like this, you got really two options on how to figure it out. I think one is a little bit quicker than the other, but there are two different ways. Obviously, 1080 degrees, that's a lot. How could you maybe start solving this problem? Good. You could divide it by 360. Honestly, I think I would subtract from 360. That way you don't have to work with remainders and stuff, but you can work with 360. 360 would take out whole circles, right? So if I take 1080 and I subtract 360, that's going to be 720. And if I take 720 and I subtract 360, that's going to give me another 360. So what you're trying to do is you're going to subtract, we're going to put over here option 1, subtract whole circles until your answer is between 0 and 360. And then you're just going to check to see if that's a multiple of whatever you divided it out. So in this case, a multiple of 90. So if this is a multiple of 90, then it would map the figure onto itself. Since this one happened to be 360, you can go ahead and know that the answer is yes, because 360 is going to always map something onto itself. So is it a multiple of, and then I'm just going to draw this arrow up here, because it's not always going to be 90. It's just going to be whatever this calculation came out to. So that is one way to do it. There is another way. Anybody got a different idea? If you do subtraction repeatedly, another thing that you could do is to divide. And I like this one better. But instead of dividing by 360, if I just divide by the degree of rotation from one corner to the next, in this case, that's 90 degrees. So divide by the degree, the smallest degree, sorry. Divide by the smallest degree of rotational symmetry. So if you get a whole number answer, that means that that point that you're starting with has jumped exactly that many times all the way around, and it's going to wind up on another point. So if I take 1080 and I divide it by 90, let's say that'd be 4, 8, 12. I think that's 12. I should probably check that. But what that means is 1080 degrees is going to move that point, whichever point I start with, 12 times all the way around the figure. So you can use that to figure out exactly where it does end up. And sometimes they ask you this on a weekly check question as well. So let's say I started at point A. 1080 degrees moves it 12 different spaces away. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. and it ends up right where it started. If it had been 13, it would have ended up there. If it had been 11, it would have ended up there, right? Because you just count them. Start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Or 12, 13, or however many numbers you get to down here. So any questions about using numbers bigger than 360? Okay, so then let's look, last couple of examples on page 105. We're going to do 7, 8, and 9, and then I'll let you work. So number 7, we are describing the types of symmetry. The two types are line and rotation, so we just take them one at a time. Is there a line of symmetry already drawn on number 7? Yeah, so we got this line right here. So we know that there's line symmetry because it's already started for us. Are there any other lines of symmetry on number 7? What I tend to do is I tend to pick a point like G, and I try to figure out where else could I match this point. And as I look around on these other corners, I don't have anything else that's going to match this. So I can fold this figure in half like this line indicates, but that's the only thing I can do because nothing else is going to match G. So I just have one line of symmetry, and it's the one that's drawn. Then I kind of take the same point and I imagine what would happen if I spin this figure. If I spin this figure, there's still nothing else that's going to match up with G. So there's no rotational symmetry. We're going to put none except for 360. So we're going to put only 360. Nothing less than 360 will work because G does not have any other matching pieces out here. Okay, let's scroll down, or not scroll, but I guess move down and look at number 9. We're going to kind of zigzag. For number 9, I tend to look at a point like T, right? I don't want to use V and W. I want to look at the point that's going to be hardest to match. So I'm considering point T on this figure. Your brain might process it differently, but that's how I do it. So first, let's look at lines. Are there any ways that I can fold this figure so that T is going to have a match somewhere else? No. So no lines of symmetry. Then we think about rotation. Middle of your figure is right about there. Is there any way that I can spin this where it's going to end up looking the exact same as it looks now? 360 is all you got. So we're going to put none, only 360. And so this one actually does not have any symmetry. Again, 360 works, but it's not really a special case because everything has 360 degrees of rotational symmetry. So it does not have any special symmetry here. Now let's look at this one. Number 8 is one of my favorite ones, but, because it really makes sure that you understand the fine details. Yes, sir. So first let's talk about lines, and heard the suggestion down the middle. So I'm going to draw that. You'll notice I'm grabbing my pencil. If I had just a regular pentagon without all these little exterior angles shooting off, that would totally work. But if this is a line of symmetry, everything on the left needs a match on the right, or vice versa. Everything on the right needs a match on the left. So I'm just going to use this point right up here, point J. Does point J have a match on this side? No. So that's actually not going to work. If it didn't have these little pieces sticking out, it would. But the shape does have these little pieces sticking out. We've got to pay attention to all of the details of the figure. Correct, it is none. So there are no lines of symmetry. Now let's look at rotations. Your middle of your figure is probably somewhere right there. And let's imagine how this would look. If you took this figure and you kind of held your finger there and you spin it, would all of these little pieces end up mapping to each other? Like, are they pointing the same direction if you spin it? If I take this and spin it down here, this would now be making this angle, right? And if I take it and spin it down here, now it's sticking out this way. Because all of these stick out the same direction, like watch, I can start up here at the top, and I'm going to extend all of my lines on the second part where I draw them, right? And so extend out, and extend out, and extend out. And all of these stick out the same way, kind of like a pinwheel. That's what it looks like to me. Because they all stick out the same way, they're going to rotate onto each other. So we do have some rotational symmetry. And we're going to take 360 and divide it by what? Mm-hmm. And if you remember from earlier, that was 72. But it's not just 72. It's every 72 degrees. If you want to list them out, you're welcome to do that. But I just write every 72. Okay, so any questions on that? All right. Then let's look at your IXL skill on that. Gina, would you mind letting Gage back in? Thank you. So, rotational symmetry. Oops, this one. Your rotational symmetry assignment, whenever it loads, look at how easy that is. Which picture has rotational symmetry? Well, it's got to be that one, right? The other ones don't have matching parts if you rotate. Which picture has rotational symmetry? Well, yeah, like this is some easy stuff. So let's jump up a level. At some point, it will stop asking you if it has rotational symmetry, and it will say that it does. When it tells you that it does, the question will always be, what is the smallest number of degrees you need to rotate the image for it to look the same? And this is where we're just dividing. So how many matching sections does this domino have? I mean, no. Take the domino as a whole. How many matching chunks does it have? It's got 2, right? It's got the left side and the right side. So we're going to take 360 and divide it by 2. You get 180. And look, there's no other level. Like, this is it. So on your tire, the details matter. The details matter. So how many different matching sections do we have here? 5. So you can count the white parts, 1, 2, 3, 4, 5, or you can count these dots, these lug nuts around the side. That's 5. So 360 divided by 5 would be 72. We've already done that a couple times today. That's how I know that. Keep going. Again, around the center, you're going to figure out how many matching parts. So how many matching parts does this one have? 6, right, because you're wanting to go around the center. So I would count 1, 2, 3, 4, 5, 6. So 360 divided by 6. And that's all you do. Any questions on that before I turn you loose? All right, get both of them to 90. If you would like to get them to 100, that'll be some extra credit.